Before I start the discussion, how do you guys feel now that the project is over? Was it hard? That's okay, Ethan. There's going to be like a second round of submissions. So if you got less than 80% on this one, it definitely will um will be valuable to submit it the second time because I think you can get up to 80 points on the second submission. Chase, that's good. That's good. Um, it's theater. I honestly I agree with you. Minesweeper was kind of harder for me too. Um, with the AVL tree, we gave you a lot of like pseudocoding classes and stuff, but Minesweeper was just here you go, tossing us into the waters and like trying to figure out how the that stupid C++ library works is also hell. But yeah, as a reminder, don't forget that you will have a second submission. So if you did bad, don't worry about it. Today, yeah, I guess Alex, it's a it's a choice for sure. Um, Today we're gonna talk about heaps and priority queues, and I'm pretty sure that at this point Professor Aman has gone over these with you guys. Let's see. First, I'm going to talk a little bit about our course policies. So just clarifying a few things. For the quizzes, in the past, they were timed and proctored, but we decided to change this for you guys and give you a little bit more time. So we keep them open for multiple days, and um, you're supposed to complete these alone, but we changed that a little bit this semester to give you the partners for programming quizzes. So when it comes to the programming quizzes, you are allowed to ask conceptual help in office hours and clarify the bounds of the problem, but you cannot show or discuss your code with any of the TAs, and you cannot do that with any of your peers either, unless they're your partner for the quiz. When it comes to STEPIC, this is meant to be a practice resource, and you can collaborate with your peers and ask any questions in the office hours about this. About discussions, so participation activities are not graded. So any of those little games that we had, they're not going to be graded. And the discussion quizzes are technically graded, but they're graded only on completion, and they're there for participation. So you need to do 10 of those quizzes to get full extra credit. For projects, you can discuss your projects with your peers conceptually. So suppose that you want to, discuss about tree rotations and deletion. You can pull out a whiteboard and draw it out with your peers to figure out if you're thinking in the right direction or not. But you cannot just write out code with other people. You can ask for both conceptual help and debugging help with office hours, but when you're asking us for help in the office hours or over Slack, make sure that you already did your part, which means that you debugged the code yourself already. Print debugging will get you far, but not nearly far enough for this class. You're gonna have a lot of a lot of data, a lot of variables that you're gonna have to keep track of, and debugger helps with that a lot. So make sure to use those. And when you come to us for help, kind of know already where the line is that's completely breaking your code and you don't know what to do with that line. Like you saw it in the debugger, that's where everything goes wrong, but you don't know how to fix that line, then you can come to us. We will not be looking at your entire project file or entire class that you built. When it comes to the test cases for the projects, you can share the like input and output of a test case with the peers, so you can create a common document that's gonna be like, oh, here are the inputs and here are the expected outputs for this for this test case, but you cannot share the catch 2 test cases because we grade you on catch 2. We cannot, those have to be unique to you. And then once again, you cannot show or discuss code with your peers. Do you have any questions about the exam before we move on? No questions about the exam? Everyone good? It's gonna be on May 1st, I believe. I'm pretty sure, yes, that it will include heaps. Uh, yeah, you will have a sheet of paper as a cheat sheet that you will have to write yourself. They have to be handwritten notes though. Uh, yeah, the questions are kind of so 70, I believe 70% of the exam are going to be the questions that are similar to conceptual quizzes, and then you'll have 30 points that are going to be pseudocode writing questions. So there's going to be 2 or 3 questions that are really there are problems you either saw or didn't see before, but you have to write the pseudocode on them on the exam. I'm not entirely sure how many days the exam is going to be open for because it really changes. It really depends on whether you're online or overflow, etc. I think you guys will have the weekend, but I'm not entirely sure about that. You're going to have to talk to Professor Aman about it. The policy on cheat sheets is you have one paper, so front and back, and you can write whatever you want on it as long as it's handwritten. Like whatever notes you need, as long as it's handwritten, you're allowed to bring it to the exam. And I think that's about as much. Wendy, I think that's gonna work. I think that works. As long as it's not like copy pasted or typed out, I think you'll be fine. Any other questions? If not, I'm gonna move on to our queues. So priority queues. What are priority queues? The idea of priority queues is like you have a regular queue. So we know what a regular queue is, first in, first out. But when you add an element into the queue, it's assigned a priority. So they're kind of ordered in that sense based on which element's gonna leave the queue. Not the priority in regular queues is based on like who entered the queue first. That's how your priority is assigned. In priority queues, you can customize that. So an element with the highest priority is DQ'd before everything else. So if you have high priority versus low priority, the element with high priority is DQ'd before the one with the low priority. Elements with the same priority are handled in the order that they enter, so those are handled the same way that a regular queue would handle them. Priority queues are an abstract data type, and that means that it will define properties and behaviors, but it has multiple implementations or multiple actual actual data structures that can construct it. So the functions that priority queues have are insert, peek, and pop. We're familiar with these from before. Insert inserts an item and it gives it a priority. Peek returns the highest priority item, and pop removes the highest priority item. The way you can implement them is with an unsorted array or list, and that gives you fast insertion, but slow extraction, because you have to like move all those elements. Once you remove an element, you have to move everything back to fit to fill in the place. And then a sorted array or a list or slow extraction in a sense that you need to find the element with the highest priority, and you have to like sometimes loop through the entire array because they're not sorted. And then once you extract them, you have to also move everything around. Sorted array, you have slow insertion because you have to find the place where to insert it and then move all the elements after it to like accommodate for it. If you have a list, that's a little faster, but you still have to find the right place to insert it at. And then extraction is faster because the first or the last element will always be the ones that you want to extract. So obviously, because we have those two complete opposites, the computer scientists were thinking, we need to find a way to balance those out. And that's what they did with a heap. Heap is a tree-based data structure that implements the idea of priority queues. So the nodes higher up in the tree, so in higher levels, they have higher priority. And priorities are assigned according to the like heap ordering property. So what that means is that in a max heap, which is priority is given to larger values, each node will be greater than all of its children, and the root is the largest element in the heap. The children, however, don't have to be ordered, and you'll see examples of it, but one node's child can be higher than that node's sibling in the tree, as long as that child is not higher than the node itself. Min heap, priority given to the smallest value, so flip them. Each node will be less than all of its children, and then the root is the smallest element in the heap. This is what they look like. So let's see. Pen. We have min heap here. Root is 10, that's the smallest element. Max heap here, 100, largest element. In min heap, all elements, all children of 10 are greater than 10, 15 and 30. And then all children of 15 are greater than 15. And all children of 30 are greater than 30. These don't have any ordering in the same level. They don't have to be ordered at all. They have no rules are applied to them except for this difference, like that this has to be smaller than this. And then in the max heap, opposite, 40 and 50 are smaller than 100, 10 and 15 are smaller than 40, 50 and 40 are smaller than 50. Moving on. binary heaps. So binary heaps are heaps that are implemented using a complete binary tree. So the ones we saw before were binary heaps. A reminder, a complete tree, it means that all the levels are completely filled except possibly the last level. So this level here doesn't necessarily have to be completely full. And the last level has all the nodes filled as far left as possible. So if we want to add more nodes into this tree to keep it full, we would have to add a node here. Extra node. Traditionally arrays are used to implement heaps, but you can build it using a tree too. It doesn't. It's very similar, and we're gonna go over some tree implementations too. Height of the heap will always be log n because it's a binary complete tree, so it's always going to be branched out. So all the operations are then log n too, because you need to you have a bushy tree. The reason pop is log n, even though you only remove this one, which you have access to, is because once you remove it, you need to replace it with something, and there comes an algorithm that you're gonna have to be familiar with, which is called Heapify, and it can be Heapify down or Heapify up depending on whether you're inserting or deleting. But once you delete the root, you have to replace it with one of the nodes, and then you shift those nodes in the heap, calling it Heapify, to reorder the elements to get back to that heap rule where the root is the smallest, and then each subsequent levels the nodes get higher. Or if it's a max heap, you flip it. Insertion is log n 2 for the same reason. Once you insert an element, and you always insert it at the very end because complete tree once again, you still have to do the heapify in case that it's that the node doesn't follow the rules of the heap. So you have to like shift it around in the heap to get it to the right location. And I told you guys that within a level, the nodes don't have to be ordered. So you will only ever go up one branch. So the insertion will always, or heapify will always be only log n. Now, array representation of heap. So it's a 0 indexed array. That means that it begins at 0. That's the one we'll use most of the time. You have also here values for a 1 index array. That means that like the first element is at 1. But because you know how C++ indexes or arrays will mostly be using 0 indexed array. So the way they're represented with an array is that you put all nodes into an array with these values for the indices. So each node, if the node is at the index I, its children, its left child is going to be at the index 2i plus 1, and right child at the index 2i plus 2. And if you invert these, if you pick a node at location I, its parent is going to be at location I minus 1 over 2. And always do the integer division, so floor the result. So suppose in this example, yeah, random access is really important for this one. Theodore. That's mostly why we use an array. So suppose you want to look at 5, our node 5 here in our array. That's 0, 1, 2, 3, 4, 5. Yes. Yeah, Alex, you're right. So 5 is at index 3. Its children would be at indices 3 times 2, which is 6, plus 1 is 7, but we don't have 7, so it'll be something like here. This is going to be the left child if we have it. So if we insert nodes, this is the location of the left child. The right child will be one after it. So the right child would be here. And then the parent of 3 or 5, sorry guys, is at 3 minus 1, which is 2, divided by 2, it's 1, 3. And when you look at the tree representation, that is correct. So parent of 5 is 3. And we have one node missing, so that's this location. And then the 2 nodes where 2 children of 5 where it would be. So it's pretty representative. Now, it's Menti time, guys. We are going to go over some of these questions in Menti. And when it comes to the participation quiz, I'm going to move it to the end of the discussion today. So the Menti code is there. And I'm going to share my screen with you guys to show you Menti. And let me know if you want me to also copy down the access code in the chat. Here it is anyway. And there's a froggy here. That's great. We all have trauma from Froggy Friday. Okay, I'm going to start. The first question. What are the left and right children of 41? And we gave you indices on this one here. Oh, yeah, that's pretty good. That's pretty good. Ooh, Sai, you are not first this time. I am shocked. Wow. Congrats to whoever took the lead from Sai. Next question. Ooh, sorry guys. Did not expect that one. Start it. Okay. What are the left and right children of 41 again? But you have a bigger array. You did better on the last one. Was the calculation too high, guys? What's up? Type in the chat if you have any questions. I forgot to add the reactions to this one. But if this is confusing, do ask questions. Oh my god. Wow. Sigh again. So first 2 questions over. We're going back to slides, but stay in Menti because there are more questions about it. Start location, where's the Menti? Okay. Give me a second. So, Heapify, no, that's not what I want. Heapify is an operation that rearranges the elements in the heap to keep to maintain the heap properties. So there are three variants: Heapify up, done after insertion to correct the heap. So it corrects the path between the inserted node and the root. Heapify down is done after deleting. So moves the way it works is like it moves the last element in the array or tree into the root and then corrects its path so it moves it down into the correct location. And then Heapify is done to turn any tree or array into a heap. So insertion, we're gonna start with a max heap here. So 50 is the largest element, and it's here. It's at the top. And this example is what I was talking about earlier, where this child is technically larger than 35, but it's not larger than 42, so it doesn't, it still keeps up it maintains the properties of a heap. Use that and move on. So we want to insert 45 into the heap. We put it at the end. So we put it at the end of the array and at the end of the tree. And then we do the heapify up. So we check if, because it's a max heap, we check if 35 is greater than 45, and it's not. And you have to, in your array, you have to do the calculation with the indices. And then we swap them if they're not. And then we check if 45 is greater than 50, and it's not. 50 is larger, so we keep it, and that's it. That's our new heap. These two are following our 50, which is still the greatest node, and 45 is larger than all of its children. 42 is still larger than all of its children, and the heap's good. The algorithm for it is given here. Be familiar with it. It's also given in your slides that Professor Rahman talked about. Now, this is a quick question. I'm not going to actually make a poll for it, but assuming that 21 was just inserted into the array or into this heap, after adjusting the nodes, so after the whole heapify thing happened, what location will 21 be in? Just type out the letters A, B, C, or D into the chat. Great job, guys. Those are all correct answers. That's so far 100% correctness in the responses. Amazing. Yeah, so it was location B. It'll be swapped with 19 because it's greater than 19, but it won't be swapped with 32 because 32 is still greater. And this is a max heap. And then 20 is a bogus location. It'll never be 20. It cannot go into this branch on insertion ever, unless it's added here. So it has to stay within the branch that it's inserted to. Deletion. So we have a mini heap here. First thing you do is you delete the root. So you remove the root, and then you replace it with the last element in the array. So that's going to be our 43. So we swap 43 and whatever the first element was, 30 something. It wasn't, it was 3. Anyway. In practice, you want to swap them first before deleting, because you can't have a blank spot in the array in code. You just swap 43 in the first element and then delete this one. And if you have a tree, you cut this connection here, so you make this null pointer. But in arrays, it's a little easier. If you have a vector, especially, you just pop the last element. So 43 is now at the top, but because we have a min heap, it's definitely not the smallest element. So what we do is that we compare it to the children. Is it greater than its left child? And is it greater than its, the other way, than its right child? In this case, it's greater than both of its children. So you pick the smallest child. So then you have to compare the children. So you compare the 7 and 12. 12 is larger, and then you swap 43 with the smallest child. In the case where this one could have been like, I don't know, 45 for some reason, and this is, I don't know, 70, you would only compare it to one child and swap it with the one that's smaller. But because both children are smaller than 45, you have to compare the children too. So you compare the children, and then you swap it with the smaller one. And now 43 is here. And then we do the same thing again. You compare it with both of its children again. If it's larger than both of them, you compare the children. In this case, 11 is less than is less than 5. So you swap it with 11. Or is less than 15, sorry. And you swap it with 11. And you're at the end. There is no, when you look at the indices for left and right children are out of bounds. So you're at the bottom, you're done. This is your final array. So this is the deletion algorithm for a min heap. And now we're going back to Menti, same code. Menti. Okay, so you guys can see it. Let's move on to the next question. And this question is, assuming this heap just removed its root, what node will take its place? And that is before Heapify. So which node will move here at the top before Heapify? Good job, guys. Great job. That's amazing. Love to see it. Yes. Oh, I love the drama of Menti. Sai, you're still at the top, but you had a very, very good rival this discussion. Whoever this is, good job. You were also smart, fastest. Jesus Christ, fastest at this question. So good job, Alex. Good job too. Everyone who's on this list, good job. Well, I guess not many of you were answering questions, but anyway, just good job in general. And before we move on, I have a surprise question for you guys. So let's see. It's a B tree. So you're represented with a perfect B tree with N3, L3, and height 2. You have a couple of reminders here. How many unique keys are in this tree? You have reminders of perfect B trees, properties. Yes, good job, guys. That's amazing. Round of applause. That's beautiful. I love to see that. I am proud of all of you. Yeah, it's still Sai. Alex, you were really close, but Sai still wins. I'm gonna have to figure out some way to get you a rubber ducky, Sai. You've been winning Menti every week. Okay, back to the presentation. So, do you have any questions so far? Before we move on to turning trees into a... Well, I guess not. I'm also gonna have to open the quiz for you guys soon. Let me do that real quick right now. Break. Quiz break, quiz break. If you have any questions for me, write it in the chat right now while I'm doing this. I was really struggling with Wi-Fi this morning and I had no time to do any of it.